Good morning, students. Today we are discussing the armature reaction in the DC machines. Basically, throughout the lecture we will be covering the details of armature reaction particularly in the DC machines, then what are its impacts, its impacts on the performance of DC machine, and then if they are not so good, then how they can be minimized, how the effects can be minimized. So, I am just starting with what is armature reaction. As you know, the DC machine is a doubly excited machine. Machine has mainly two parts, one is field, another is armature. The purpose of field in the DC machine is to provide the requisite flux density for the machine working, and the purpose of armature is to carry the required amount of current through its conductor, which is necessary for the electromagnetic interaction. Then it is producing the flux, magnetic flux, it is carrying the current. But if we consider that when current passes through the armature conductor, they also produces their magnetic effect, then how this magnetic flux produced by the armature conductors interacts with the field flux. So, there the topic armature reaction evolves. So, basically we can define the armature reaction, the effect of armature flux on the main flux or the interaction of armature flux with the main flux or field flux, it is called as armature reaction. So, armature reaction is basically the flux which is produced by the armature conductors or due to the armature current in the armature conductors. When it interacts with the field flux, this interaction is named as armature reaction, right. So, in the coming diagram I will be explaining how the field flux, then how the armature flux, and how the resultant flux will look like. So, in the first diagram it is the field flux when we are not considering the flux imparted or flux produced by the armature conductor. It is a diagram of two pole machine, north and south. The flux is emerging out of the north pole and it is entering into the south pole. So, it is from north to south the flux is travelling. Now, in the second diagram I am just considering the effect or the flux produced by the armature conductor. If we look at the armature, then the conductors are divided into the two halves along the geometrical neutral axis. In the left half, that is the conductors falling under the north pole, they are carrying current inside the plane, and the conductors which are falling under the south pole, they are carrying current outward of the plane. So, in the left half the conductors are shown with the cross, and in the right half the conductors are shown with the help of dots, right. Now, if we draw the lines of flux around these conductors, then these lines of flux will be the concentric lines, and the direction of these concentric line can be found with the help of right hand thumb rule. So, if I hold the conductor in the right hand such that the thumb point out towards the direction of current in the conductor, then the curved finger will indicate towards the direction of magnetic flux around the conductor. So, I have just hold the conductor pointing the thumb in the direction of current, then the curved finger in the clockwise direction, they indicates the direction of flux. Similarly, I have drawn or the lines of force they have drawn on the right half, that is the conductors falling under the south pole. So this is the flux produced by the conductors. They are concentric lines, it is like this, and then in the right half it is in the clockwise direction, in the left half it is in the anti-clockwise direction. Now when the machine works, the field flux is there and the armature also carries the current. Now while working of the DC machine, the field flux is also there, armature flux is also there, then the resultant flux looks like this. This flux distorts from the main flux. If we look at the main flux, then main flux was like this. Now just adding the effect of armature reaction, the total flux looks like this. If I consider the effect, then in this quadrant, that is the left top corner, the flux is in the direction. So here the flux density is increased because the direction of flux produced by the armature and the direction of flux produced by the field is in the same direction. So flux density is increased in this half, and in this half the flux is just opposite to the field flux. That is why the flux density is decreased here. Similarly, here the flux density is decreased and here the flux density is increased. So we can say the flux density is more at this part and at this part, and it is less on this two parts. So if I draw the resultant flux density, then it looks like this. It is more in this part and it is less in these two parts. So if I summarize the effect, if I look in the diagram, then lines of force, they are close in this half and in this half, and the lines of force, they are quite far apart in these two parts, which shows that the flux density is less in these two parts and it is more in these two parts. So it is basically how the field armature flux is interacting with the field flux on a broader part. It is on a broader part. So if I say about how the armature flux affects the field flux or impacts on the field flux, then the effects can be effects may be categorized into two categories. One is the cross magnetizing effect, another is called as the magnetizing or demagnetizing effect. So in the two parts, it is magnetizing. It is in these two parts, the flux is opposing the field flux, so it is demagnetizing in the nature. From the diagram, it is looking like the amount of magnetization is same as of amount of demagnetization, as in the two halves we are having the magnetization, that is the armature flux is adding to the field flux, and in the remaining two halves the armature flux is just opposing the field flux. So on the total, if I sum this to complete effect, then the amount of magnetization seems to be equal to the amount of demagnetization. But actually it do not happens like this. Let us have a look how the magnetization and demagnetization works and how the detailed flux density will look like. So in this diagram, again it is a two pole machine, that is south and the north. Now the flux density is uniform under the pole, that is the flux density from this point to this point is constant, that is under the pole the air gap is constant, that is why the flux density is also constant. Then after the pole tip, the air gap suddenly increases and the flux density start decreasing. Then after the geometrical neutral axis, when the flux density becomes 0, the flux started increasing in the opposite direction, that is it is the zone of north pole. So flux density in the north pole will be just opposite to the flux density of south pole. So flux density is increasing in the opposite direction. Opposite direction means that the direction of flux is just opposite to what we have considered in the positive part. So again from the pole tip to pole tip, the flux density is constant, and then after finishing the pole tip, the flux density again start decreasing and it reaches to 0 at the geometrical neutral axis. So it is the flux density produced by the field. Now we are considering the armature MMF and then the armature flux. So armature MMF is basically the number of turns into the current carried by the armature conductor. So the armature conductors, they are on the armature periphery. So if I calculate the effect, or if I draw the armature MMF, then N into I at the center of pole, the number of coils enclosed by the lines of flux of armature, it is just 0 or it is minimum. That is why the armature MMF is minimum at the pole center. It is minimum at the pole center. Then the direction of lines, it is upward. It is upward. So MMF is increasing in the positive direction, but on the left side of this conductor, the direction of magnetic lines of force, they are downwards. So flux is, or armature MMF is increasing in the opposite direction. So it is increasing till the geometrical neutral axis, because at this the lines of force are enclosing the maximum number of conductors, and these maximum number of conductors multiplied with the armature current will give you the armature MMF, which is maximum at the geometrical neutral axis, and then again from this it is decreasing till the pole center, and then again it is increasing in the opposite direction as explained earlier. So the armature MMF line is this, it is the armature MMF. Now the armature flux will be armature MMF divided by the reluctance of the magnetic path. So under the pole, that is from this point to this point, the air gap is uniform. So when the air gap is uniform, the reluctance provided by this air gap is also uniform. So the armature flux is definitely less than the armature MMF, but it is also varying in the same manner as of armature MMF. So armature MMF divided by the reluctance of the air gap under the pole, so it is less, but it is following the same pattern as of armature MMF. When the pole tips or pole finishes, after that the air gap suddenly increases. So in the interpolar area, the air gap suddenly increases, and that decreases the armature flux in the interpolar area. So even if we are having the maximum armature MMF in this area, the armature flux is quite less in the interpolar area, just because of the air gap is quite large as compared to this air gap, and that is why the flux is decreased considerably in the interpolar area, and we observed dip in the flux. Now again from this point to this point, the air gap is constant. So the reluctance provided by the air gap is also constant, and the flux is following the same pattern as of MMF, but of course the flux is less than the MMF, as flux is MMF divided by the reluctance. So now we are having the two fluxes. One is the field flux, right, and then is the armature flux. This is shown by the dotted line. This is the armature flux. So, in order to draw the total flux or the resultant flux, I need to add this flux and this flux. So, I need to add this flux and this flux is the armature flux and this is the field flux. So, if I draw the resultant flux, then how it looks, let us have a look. This was the field flux shown by the dotted lines. Now, if I add the armature flux to the field flux, then I am starting with this point. The flux density is somewhat existing in the negative direction and here it is 0. So, 0 plus something in the negative direction, the resultant is also in the negative direction. Now, the flux is in the negative direction and here it is in the positive direction. So, somewhere the positive fluxes and the negative fluxes, they will be equal, then the flux will cross through the 0. Flux will cross through the 0 when these two flux densities in the opposite directions will be same. So, it will cross through the 0 and then it will increase in the positive direction or in the direction of field flux. So, it is increasing in the direction of field flux. Now, if I look at the under the pole, then in the first half of the pole, that is in this half, this point to this point. So, in this half basically the armature flux is opposite to the field flux. So, the resultant flux will be less than the field flux. It is the field flux and it is the resultant flux. So, resultant flux is less than the field flux, original field flux, because the armature flux is just opposite to the field flux. Then at the pole center, the armature flux is 0. So, pole center it will cross to the original field flux and then in the second half of the pole, the flux density or the flux direction of flux by the field and the direction of flux by the armature is same. It is also positive and it is also positive. So, they are adding each other. They are adding each other. So, it is more than the field flux. So, it was the original flux and this is the resultant flux, that is more than the original flux. Then it is again decreasing because it is also decreasing and it is also decreasing, the overall flux will decrease. But again at the geometrical neutral axis, when the flux density by the field was 0, it will not be 0 here, just because of armature flux is not 0 at this point. So, this armature flux will create some flux density at the geometrical neutral axis, and then the flux density after the geometrical neutral axis, the field flux started increasing in the opposite direction and the armature flux is still in the same direction, but somewhere they will cancel each other and there it will crosses through the 0. So, it will crosses through the 0 at the point D, where it was crossing the 0 at point C earlier, when we have not considered the effect of armature reaction. So, it is crossing through D at 0 flux density in spite of C. This is the major part we need to consider. Ki now the 0 flux density position of the machine has been changed. The 0 flux density position earlier, when we have not considered the effect of armature reaction, was C, and now when we have considered the effect of armature reaction, it is now D. So, first effect that we have investigated, that is the shift of neutral axis. Earlier the geometrical neutral axis was the magnetic neutral axis. That means along the geometrical neutral axis, the 0 flux density was aligned. But when we have considered the effect of armature reaction, then the zero flux density position has been shifted by some angle which is known as the theta angle, which is known as theta angle. So, the angle has been shifted, and this angle of shift will be in the will be in forward direction when the machine is working as a generator, and it will be opposite to the forward shift, that is in the reverse direction when the machine will work as a motor. So, the theta have shown here also and here also, because here we are talking about the machine, not specifically about the generator or motor, but definitely this shift will be in either of the direction depending on how the machine is working, whether as a generator or as a motor. Then there is one important impact. This is the area which I have shown by a hatched line, that is the flux density is decreased due to the saturation, and it is called as the demagnetizing effect of the armature reaction. So, how this demagnetizing effect of armature reaction works, let us have a look. So, the demagnetizing effect of the armature reaction could be can be explained with the help of this diagram. As I told that in the first half of the pole, the armature flux was in the opposite direction as of field flux, so it was producing the demagnetizing effect. And in the next half, or in the second half, the armature flux was in the same direction as of field flux, so it was magnetizing in nature in the next half. But if we know very well that whenever we design the machine, the magnetic, just to utilize the full capacity of magnetic material, it is magnetized up to the knee point of BH curve. So, in this particular machine, I considered that the machine is already magnetized up to the point or up to the flux density B naught. So, this is the original flux density provided or produced by the field flux. Now, I am including the demagnetizing effect and then the magnetizing effect. So, I am including the effect by the same amount, that is by the amount of HA. So, HA is same in the positive direction as well as in the negative direction. It is the demagnetizing effect and it is the magnetizing effect. So, if I project these 2 points, that is suppose this point is X and this is Y and this is Z, then if I project the point Y on the BH curve, then it is at this point, and if I project the Z point on the BH curve, then so now the amount of magnetization and demagnetization was equal on the X axis, that is it was by the same amount HA. But when we reflect on the Y axis with the help of BH curve, then the new flux density comes out to be B1 and B2. So, it is very clear from the diagram that the amount of magnetization was B1 minus B0. This is the amount of magnetization, and the amount of demagnetization is B0 minus B2. So, it is amount of demagnetization. So, it is very clear that B0 minus B2 is greater than B1 minus B0. So, it is very clear that the amount of magnetization is less as compared to the amount of demagnetization. So, net effect of armature reaction will be demagnetizing in nature, because it is magnetizing by this amount and it is demagnetizing by this much of amount. So, demagnetization is definitely dominating over the magnetization, and the net, if we calculate the net effect comes out to be the demagnetization. So, it is called as the demagnetizing effect of armature reaction, which means that the net flux density in the machine decreases because of armature reaction when we include the effect of saturation in the material. If we do not include the effect of saturation, it just happened because of we have included the saturation in the material. If we are not considering the saturation in the material, then surely this will not happen. If I am on this point or the material is magnetized in the linear region only, it is not magnetized till the knee point, then surely this demagnetization will not happen. But practically in all machines, the machine is magnetized till its knee point, so that the magnetic material could be utilized in its full capacity. And when we consider the armature reaction in the practical machines, then this armature reaction visualized net in the demagnetization, that is the flux density in the machine decreases, net flux density decreases in the machine because of armature reaction. So, the demagnetization is shown in the diagram by this hashed area, that is the flux density is decreased by this amount due to the saturation. So, reduction in flux density due to the saturation, and if we do not consider the saturation, again I will be telling you there will not be any kind of demagnetization in the DC machine. So, it is an important effect which reduces the amount of induced EMF that will be developed in the DC machine when the flux density is decreased considerably. Now again, this amount of demagnetization will depend upon the magnitude of armature flux. So, armature flux, if it is more, then the amount of demagnetization will also be more, and if the amount of armature flux is less, then surely this amount of demagnetization will also be less. So, this is the demagnetizing effect I have shown earlier. So, if I summarize the effect of armature reaction, then the effect of armature reaction can be summarized into two parts. One is called demagnetizing effect and another is called as the cross magnetizing effect. So, demagnetization I have explained. Now, what do I mean by the cross magnetization? So, cross magnetization actually indicates the flux density along the geometrical neutral axis. I have explained earlier that the neutral axis of the machine has been shifted by the amount theta just because of the existence of armature flux in the interpolar region. In the interpolar region, some flux density is there, and because of this flux density, the zero crossing of this flux density has been shifted. So, the development of flux in the interpolar region is called as the cross magnetizing effect of armature reaction. Another part, on the another part, earlier the flux density was uniform under the pole. It is uniform under the pole, but now if we consider the armature reaction, then flux density is now not uniform under the pole. It is increasing in the one half and it is decreasing in the another half. So, flux density has been changed because of armature reaction, and the development of flux in the interpolar region are the two main effects under which will be considered under the cross magnetizing effect, or we define the cross magnetizing effect, then the overall flux density over the periphery of armature has been distorted because of armature reaction. Under the pole, it is not constant now, and in the interpolar region, some flux density is existing due to the armature cross flux. So, this is the effect that we can investigate from this diagram of the armature reaction. But what are the actual impacts of armature reaction on the performance of DC machine? That we are going to discuss. So, the detrimental effects of armature reaction on the performance of DC machine are investigated as three. One is the increased iron loss, second is the bad commutation, and third is the increased cost of field winding. So, first, increased iron loss. As you know, the iron loss, which comprises of hysteresis and eddy current loss, they are proportional to the maximum flux density in the DC machine, in any type of machine. Then maximum flux density is increased, you know, earlier it was B0 and now it is B1. So, the maximum flux density in the machine has been increased due to the armature reaction. Then corresponding to this maximum flux density, the iron losses will also be increased in the machine. So, this is the first effect. When losses have been increased, definitely they will affect the efficiency of the machine. So, increased iron loss will decrease the efficiency of the machine under the loaded situations. Now, second point is the bad commutation. What we mean by the bad commutation? The bad commutation means the commutation is not sparkless. The sparking is developed between the commutators and the brushes when the coil undergoes the process of commutation. So, why this bad commutation is there? Let us have a look. As I told that the flux density is not 0 along the geometrical neutral axis and the brushes are located, the brush is located along the geometrical neutral axis. So, coil which is undergoing the process of commutation, it is not located under the 0 flux density position. Now, it is located under some flux when it is undergoing the process of commutation, and because of this flux density, a rotational EMF will be developed in the coil which is undergoing the process of commutation, and if this EMF exceeds from 30 to 40 volt between the two adjacent segments, then the sparking is developed between the commutators and the brushes, and it is nothing but the bad commutation. And if this sparking is so aggressive, then the sparking may form a fire ring around the complete commutators. So, this is the severe effect of armature reaction that can be visualized while the performance of machine. Third is the increased cost of field winding. As I told that the armature reaction decreases the amount of flux in the DC machine because of its demagnetizing effect. Now, to maintain the same flux under the consideration of armature reaction, either we need to provide more number of turns on the field winding or we need to provide more current in the field winding. On either of the part, they will increase the overall cost of the machine. So, third effect is the increased cost of field winding or the increased cost of field current. So, these are the main three effects, bad effects, or we can say the detrimental effects of the armature reaction on the performance of DC machine. But always keep in your mind that these effects will not be visualized under the no load situations or the lightly loaded situations, because all these three effects are proportional to the armature flux. That means, if the armature flux is very small, then these effects will be very small, or they may not be there. On the other part, if armature flux is considerable, then these effects will be severe, and the armature current is directly proportional to the load current in the DC machine. So, these effects can be said proportional to the load. So, armature reaction is always severe under the loaded situations, not under the no load or the lightly loaded situation of the machine. So, the effects are there, and the effects are severe only when the machine is loaded. Now, we have discussed about the problems that have been evolved due to the armature reaction. Now, in the next part, we are discussing about the methods of minimizing the effects of armature reaction. While designing the machine, we can't be quite okay, the armature reaction is going to happen and we will see and then we will do something. No, all these effects are to be taken into the account prior to the working or at the time of design of the machine, because once the machine is designed, very small changes are possible in the machine. So, we will be taking into the account how these effects can be minimized. But again, this will depend on the size of machine. All these solutions cannot be applied to every machine. So, these solutions will depend on the size of machine. If the size of machine is too large or too big, then in that case we need to opt the costly solutions, and if the size of machine is very small or it is medium, then amount of armature current will be less, correspondingly the amount of armature flux will be less, and these effects will not be as severe as in the larger size machine. So, I am talking about the methods, but these methods works from smaller to bigger, that is the prior solutions are applicable to the smaller sized or the mediocre sized machines, but when the machine size is too big that the armature reaction cannot be handled by the prior solutions, then surely the last or the these solutions will work. So, the first solution is by using high reluctance pole tips. So, first what do we mean by the high reluctance? So, it is explained here. In the diagram, I have considered that under the pole the air gap is uniform. So, if the air gap is uniform under the pole, the reluctance provided by the air gap will also be constant. But if we look at the in this diagram, the effect of armature flux is very less in the center of the pole, but it is quite high under the pole tips. Under the pole tips, the magnitude of armature flux is quite large. So, if we can increase some reluctance on these tips, just on the tips, not at the center part, because at the center part it is already very less, it is already less, at the tips it is more. So, if we can increase the reluctance by increasing the air gap at the pole tips, it is clear that at the pole tips the air gap is slighter more than the center. So, if we can design the high reluctance pole tips by providing more air gap at the tips, then the amount of armature flux will be decreased at the tips, and the relevant distortion which is produced by the armature flux will also be less. So, the first solution is by increasing the air gap at the tips. This will decrease the magnitude of armature flux and further the effect of armature reaction. So, and this can be done by chamfering the pole faces through the file, and it can also be done by using such type of poles, that is they are having air at the tips and no air in the center of the pole. So, this is the first solution. Then second solution is decreasing the armature flux itself. So, how the armature flux can be decreased? So, these are the punched poles, the air gap is existing between these poles. Now, when the armature flux will complete its path through this, then this air gap will increase the reluctance of the path and further the magnitude of flux will be decreased. So, the armature flux can be decreased by using these punched pole construction. This is the second solution. Third is by developing the strong magnetic field. It is the natural answer. Whenever we need to fight with the enemy, we need to be more strong. So, if field flux has to fight with the armature flux, then obviously the field flux has to be more strong, and if the field flux is made more strong, then obviously the effect of armature flux will be or could be neglected in comparison of the magnetic field. But this again involves the cost of field winding as the cost, or also the cost of the field current. So these are the three simple solutions can be opted in the smaller as well as the mediocre sized of machines. But when the size of machine is growing or size of machine is large, then the earlier solution may not work. The earlier solution may not work, and the effects which are investigated due to the armature reaction may not be minimized. Then these two solutions, that is by employing the interpoles. Interpoles are the small capacity poles located in the interpolar area, that is the area between the two main poles, and these small poles provides the flux density just opposite to the armature flux, so that the net flux in the armature interpolar area, suppose I connect one pole here, and this pole produces the flux density in such a way that this flux is nullified. So flux can be nullified with the help of flux only. So this flux can be nullified with the help of flux produced by the interpoles. So this will be the solution provided by the interpoles. And last is the by employing the compensating winding, that is the compensating winding is the winding located on the pole faces, but they carries current of the armature. So they produces the same effect as by the armature conductors, but in the opposite direction, so that the flux density under the pole becomes uniform. This is employed in the DC machine when the load fluctuations on the machine is quite frequent and quite severe. So amount of load fluctuations are more and they are quite frequent in nature. In that case, we need to opt this option, that is we need to employ the compensating winding in order to minimize the effect of armature reaction. At the last, these are the diagrams of interpoles. These are the small poles between the two poles, and this is the compensating winding located on the pole faces, and they are connected to the armature so that they can carry the same current as of armature, and they can further produce the same effect as produced by the armature, but in the opposite direction to the armature flux, so that the overall effect of armature flux could be nullified with the help of compensating winding. But again, this is this last and final solution, and it is opted only when the size of machine is large or the load fluctuations are quite severe, because the cost of employing the compensating winding is very large. So normally we do not go for, but whenever the requirement is felt, this is the ultimate solution. We do not have any solution out of that. So this is the end of this class, that is the armature reaction in the DC machine.